Assalamualaikum and greetings to all. I'm Nurul Aini binti Jaafar from Department of Mathematical Sciences, Faculty of Science, Universiti Teknologi Malaysia. I am going to present my research entitled Dispersion of Solute in Casson fluid through a Stenosed artery with the effect of body acceleration. In this video, I will share about introduction, objectives, literature review, methodology, solutions, result and discussion, conclusion, and future research. Do you know that, according to World Health Organization, WHO, the cardiovascular diseases such as heart disease and stroke were the major cause of the death in the world? The cause of cardiovascular diseases is because of the narrowing of the artery diameter called atherosclerosis or stenosis. Stenosis caused by the build-up of fats, cholesterol, and other substances. So, for your information, one of the treatments to treat these cardiovascular diseases is by injection of the drug into the blood flow. Have you ever imagined that? What happens if the drug is injected into the blood vessel? Then imagine what happens if the human body is exposed to body acceleration or motion in a variety of situations, including vibration therapy for a heart disease patient, passenger water or air transport, fast body movement in athletic activities, and so on. The problem area may be the dose of the drug is not appropriate. What happened to the dispersion of drug when the body acceleration exists? What is the suitable fluid model that we can consider to describe the blood behavior for the real case? Therefore, from mathematical modeling, we can know the behavior of the drug dispersion in blood flow. Thus, this research investigates mathematically the dispersion of solute in blood flow in stenosed artery with the effect of stenosis and body acceleration. Why we did this research? This research is made to solve all the issues that I told before. This research is useful to determine the solute dispersion process, to get better fluid model data, and to get more realistic application. From the figure of blood rheology, the blood can be modeled as Newtonian fluid for large diameter and for small diameter of artery. It can be modeled as non-Newtonian fluids. In my research, I consider the blood as Casson fluid model. Why choose Casson? Suitable for small diameter arteries, low shear rate, better prediction, can be reduced to Newtonian fluid model assumption for large diameter artery. The objectives are to formulate fluid model of Casson fluid, to investigate the behavior of blood flow in a stenosed artery with the effect of body acceleration, to solve the unsteady convective diffusion equation. This is the stenosis figure. We can see that the stenosis affects the blood flow and it is very dangerous when it stands to severe stenosis. The effect of stenosis on the solute dispersion with the effect of body acceleration has been not studied by anyone so far. The geometry of the pipe describes the artery. This blood is treated as Casson fluid and it is suitable for small diameter artery. In the case of small artery, there occurs two blood behavior, thus the region of the blood is divided by two regions, blood flow at the center and outer flow near the wall. The governing involved in the study are momentum equation, it is to know the blood movement. Constitutive equation, it is to know the blood rheology. Convective diffusion equation, it is to know the drug dispersion. Method used in this study is by referring Gill and Sankara Subramaniam, 1970. The solution is assumed in derivative mean concentration. Substitute the solution into convective diffusion equation. The generalized dispersion model has been formed as follows. These are the solutions obtained in this study. Integrating the momentum and constitutive equation, the velocities in outer and blood flow regions have been obtained as follows. Then, the mean velocity is obtained to use in convective diffusion equation. By using generalized dispersion model mentioned before, the dispersion functions for steady has been obtained as follows. Now, let us look at the result. The effect of stenosis, slip velocity, and body extraction on velocity is graphically computed in this section. The results of velocity and mean velocity are obtained and discussed by fixing various parameters in the flow analytic expression after solving the momentum equation and defining the yield stress. Figure 1 shows variation of velocity u for different values of yield stress in the blood flow with A0 equal to 2, omega equal to 1, T equal to 1, V1 equal to 0, P equal to 2, A equal to 1, B equal to 2, Z equal to 3, and B equal to 2.5. The increment of yield stress 0.1 to 0.5, the velocity decreases. As yield stress increases, the amplitude of velocity falls, allowing the blood flow to image. Yield stress is significant in viscoelasticity modification because it works as a path for human blood to circulate. Figure 2 shows variation of velocity u for different values body extraction A0 with omega equal to 1, T equal to 1, V1 equal to 0, tau 1 equal to 0.1, P equal to 2, A equal to 1, P equal to 2.3, Z equal to 3, and B equal to 2.5. The velocity increases when the body extraction increases as the cross-sectional area narrows. The impact of body extraction on blood flow is to increase flow rate while lowering artery resistance to flow. Figure 3 illustrates variation of velocity u for different values of slip velocity us with A0 equal to 0, omega equal to 1, T equal to 1, V1 equal to 0, P equal to 2, A equal to 1, P equal to 2.3, Z equal to 3, and B equal to 2.5. When slip velocity increases, axial velocity increases as well. Increasing of slip velocity lead to decrease in flow resistance. The purpose of analyzing the steady dispersion function in this study is to observe the change of the steady dispersion when the input of yield stress and body extraction increases. Figure 4 shows the variation of steady dispersion function F1s for different values of yield stress, tau y, in the blood flow with A0 equal to 0.5, omega equal to 1, T equal to 2, V1 equal to 0.02, P equal to 1, A equal to 0.01, B equal to 0, and Z to 0.05. When yield stress increases, the steady dispersion function decreases near the wall and opposite behavior at the center of artery. Casson fluids are non-Newtonian fluids with a yield stress, making them ideal for narrow arteries. It is due to the flow rate of Casson fluid decreases as the viscosity of the fluid increases and the value of dispersion function decreases. Figure 5 shows variation of steady dispersion function F1s for different values of body extraction A0 in the blood flow with omega equal to 1, T equal to 2.8, V1 equal to 0.01, P equal to 1, tau y equal to 0.01, A equal to 0.01, B equal to 0, and Z equal to 0.05. The dispersion function increases as the amplitude of body extraction increases at the center of artery and decreases in the outer region near the wall. As the amplitude of body extraction increases, the blood flow drops, causing the dispersion function to decreases and the solute dispersion to be impacted by the fluctuating blood flow. In conclusion, we can say that Casson fluid model is suitable model and more realistic and specific cases is required to get better data in dispersion of solute in blood flow through a small diameter stenosed artery. And my suggestion for future research are, we can add more applications such as MHD flow that use other fluid model, and in engineering field, they can do experiment and compare the result by our data. And one more future research is can add the effect of heat transfer in blood flow. That's all my presentation. Thank you.